Hello everyone. This one is our assignment 7, calculus of complex function where complex integration. On the complex integration, just two examples given there. Remember, there are three theorems that we have. Three theorems that we have in complex integration. For complex integration, the first theorem, the first theorem is known as this Cauchy's theorem. This is a Cauchy's theorem, and Cauchy's theorem gives us integral of f z dz over the curve C as a 0. So this is the best theorem for us, but generally it comes for 1 or 2 mark question only, because yes, just we have to observe that given function f of z is a differentiable, that is analytic on and within the curve C. This is the important condition. If our f of z function is a differentiable, that is analytic function on and within the curve C, then integral value of that f z dz is always 0. So that is the simplest thing. No need to evaluate that integral. Directly we can say the value should be 0 by the Cauchy's theorem. So that about the first theorem that we have. Second theorem is known as Cauchy integral theorem. Cauchy integral integral theorem. Now this theorem works only when we have a simple pole. Now what is the meaning of simple pole? We have a function is not differentiable at a point, but that point is a pole of order 1. Okay, whenever the pole is of order 1, it is applicable, or for a simple pole we say. So in such a case, we have to consider except that pole remaining function we should be take as fz. So we have integral fz upon z minus a. Now this is f of z upon z minus a, where z equal to a is a pole. That pole should be on or within the curve C. On or within the curve C. So integral of fz upon z minus a dz is 2 pi I into f of a. 2 pi I into f of a. This is the shortcut formula given by a Cauchy, and that says integral of fz upon z minus a dz over the curve C is a 2 pi I into f of a. But I will tell you that this Cauchy integral theorem is a particular case of the third, which is known as a Cauchy residue theorem. So you can solve all the examples of Cauchy integral theorem by a residue theorem. And yes, it should be considered in the exam. Obviously, when the question 99% of the time the name of the theorem will not be mentioned, just question will be evaluated. Okay, so that time you can use a Cauchy residue only. So all the examples, yes, you can do it by Cauchy residue theorem only. So which tells us that integral fz dz over the curve C is 2 pi I into sum of residues. So we'll denote the residues like R1 plus R2 plus R3 and so on, whatever the residues we have. So Cauchy residue theorem is can be used for all types of the poles. The pole may be the simple pole, or it is a pole of order more than one. Then also we can apply this Cauchy residue theorem, and you can solve each and every example by the residue theorem. Only for each pole which is on or within the curve C. Remember, only those poles which are inside the curve C, for that we have to calculate the residues, and we can say then 2 pi I sum of a residue is the answer. But for this, yes, you should remember the formula for residue. The residue R is a given by 1 upon n minus 1 factorial. What is n? N is the order of a pole. 1 upon n minus 1 factorial, n minus 1th derivative, n minus 1th derivative of that z minus a raised to n into fz at z equal to a, provided z equal to a is a pole of order n. Z equal to is pole of order n. So these are the three theorems that we have. So I suggest you should be focused mainly on Cauchy's theorem and Cauchy residue theorem. That is enough to solve all the example. Yes, you can solve the example by integral theorem whenever we have a simple pole. So choice is your only. So let me do the first question, where we have integrate cos pi z upon z square minus 1 over a rectangle. So we'll come to the first example here. So the first example is evaluate, okay, evaluate this integral of cos of pi z upon z square minus 1. Remember, z square minus 1 have the factor z minus 1 into z plus 1. Okay, so this is the integral that we have to evaluate. Over a rectangle, the rectangle have the vertices we are given 2 plus or minus I and minus 2 plus or minus I. So these are the four vertices we are given. If you see, the diagram is not compulsory in the exam, but yes, you should know whether poles are inside or the outside the region. Generally, the closed region is a circle. In this case, we are given a rectangle whose vertices are like 2 comma 1. So say this is a 2 comma 1. This vertex, let I assume as a minus 2 comma 1. Okay, so we have the straight line here. Then we have next vertex as minus 2 minus 1, and last is say 2 minus 1. So this is the last vertex. So again, we have the straight line here. So this is the rectangle, and that we have the curve C. So this one is our curve C. So curve C is here. Okay, and obviously the region, we have a region which is inside it. So this is the region. So on this region we have to check, this is on and within. So this is our region where we have to check whether our uh, poles are inside that region or that outside the region. So inside the rectangle or outside the rectangle, that we have to check mainly. And to check it, yes, obviously we have z equal to 1. You'll observe the z equal to 1 and z equal to minus 1 are the pole. And if you observe that poles z equal to 1, so that means x is 1, y is 0. So here is the first pole 1 comma 0. Next pole is minus 1 comma 0. Yes, both are inside. Both are inside. Remember, both are simple pole. That pole is of order 1. Because of that, you can apply the integral theorem or residue theorem. Both theorems will work there. So here z equal to 1 and z equal to minus 1 are are simple pole. Simple pole means pole of order 1. Simple pole, and most important thing, inside region. Inside the region. So whenever you write inside the region, yes, you have to calculate the residues for them. Okay, or you have to apply the integral theorem for each of that. So that way you can solve the problem. So the first important note you should write that which of the poles are inside the region, inside the region. So both the poles are inside here, and now we have to evaluate this integral. To get that integral, now the first way I will show you it by residue theorem. Okay, I will show you it by residue theorem. So uh, I will take the first residue. Let R1 is a residue at z equal to 1. If z equal to 1 is there, remember 1 upon n minus 1 factorial, which is 0 factorial is 1, n minus 1 means 0th derivative. So we left with only z minus 1 into fz at z equal to 1. At z equal to 1. So z minus 1. So this is our entire fz. Entire fz is complete integrand. So that z minus 1 factor gets cancelled, and we left with cos of pi z divided by z plus 1 only, and at z equal to 1. So obviously if we replace z by 1, we get cos pi upon 2. Is it? Because we are replacing z by 2. Cos of pi upon 2. Cos pi is minus 1, so it is minus 1 by 2 is the value of R1. Now let me calculate exactly similar with R2. Okay, R2. Now let R2 is a residue at z equal to minus 1. So we get z plus 1 as a factor now into fz at z equal to minus 1. In this case, z plus 1 factor gets cancelled, and we left with cos pi z upon z minus 1 at z equal to minus 1. And similar to that, if we replace z by minus 1, remember cos of minus theta is a cos theta. So numerator again coming cos pi. Cos pi is a minus 1, a minus 1 upon minus 2. So you will get 1 by 2. The final answer for R2 is 1 by 2. Hence, the final answer by Cauchy residue theorem. Therefore, by Cauchy residue theorem, integral fz dz over the curve C is a 2 pi I r1 plus r2 in this case. Only two residues are there. So 2 pi I, R1 is minus half, R2 is a plus half. Hence, they cancel and we get integral fz dz is a 0 by Cauchy residue theorem. So this is the first way. Let I because few of the students are doing it by Cauchy integral. So let I explain in short for this example only how to do it by Cauchy integral. For Cauchy integral also, the first part you should do it. First part you should do it uh, as you have to tell that z equal to 1 and minus 1 poles are inside the region. So I'm saying here or it is for Cauchy integral theorem. So our aim is to evaluate this integral cos of pi z upon z minus 1 into z plus 1 dz over that rectangle. That C is a rectangle here. So first thing what you have to do it, you have to find out the partial fraction for the denominator linear factor. So 1 upon z minus 1 into z plus 1 is equal to, let me assume that a upon z minus 1 plus b upon z plus 1. So find out a and b. So if we find z equal to 1, so you get 1 by 2. So 1 by 2 upon z minus 1. When to get b, we will replace z by minus 1. So minus 1 by 2. So minus 1 by 2 upon z plus 1. So indirectly this 1 by 2 is coming common and we left with 1 upon z minus 1 minus 1 upon z plus 1. So this is the partial fraction. So first step whenever you have to use a Cauchy integral theorem is a partial fraction. So by partial fraction, what we are doing, we are keeping just one factor inside the region, Right now, two poles are inside, but integral theorem is not applicable for more than one pole. So there should be a simply one pole, and that should be a simple pole again inside the C. Then only we use Cauchy integral. So this integral can be converted as integral 1 by 2 cos of pi z upon z minus 1 over the C plus, not plus now, this middle sign is a minus. So minus integral 1 by 2 cos of pi z, here is a dz there, cos of pi z upon z plus 1 dz over the curve C. So same curve. Okay. But now by Cauchy integral theorem, we know Cauchy integral theorem is integral fz upon z minus a. If fz upon z minus a is there, it is a 2 pi I f of a. So this 1 by 2 is there as it is, but there is a 2 pi I into f of a means cos of, so what is a? A is 1 here. So it is cos pi. This is by Cauchy integral theorem. Minus this 1 by 2 as it is. Again 2 pi I. And here is f of 1, that is, sorry, it is minus 1 now. So f of minus 1. So cos of minus pi. Cos of minus pi. You'll observe cos of minus theta is a cos theta. First of all, this 2 gets cancelled, and you pi I cos pi and minus pi I cos pi only. So everything gets cancelled and you get a 0. So by any of the method, your answer will be the same. But only the thing you should understand how you are applying this theorem and how you are getting that answer. So I suggest you try to avoid this Cauchy integral. Better you practice one method and you should be uh, master in that method. You should have confidence in that method, and you can solve all the example by Cauchy residue only. Okay. Example 2 is exactly same. I think only small difference is there, and that is a sine square z upon z square minus 1, and circle is mod z1. Okay. Sine square z or sine of z square is there. Just 1 minute. Sine square z. Okay. So example 2, I will do in short quickly. So in the second example, we have integral sine square of z upon z square minus 1 means same factor, z minus 1 into z plus 1 over the C dz. Now if you see here, the curve C is a circle which is mod z less than 1. So in this case, our region is this one. This is inside the circle. Okay. So this is the region that we have. And for this we have z equal to 1 and minus 1. You'll observe z equal to 1 will be that is means x is 1, so this is 1 comma 0, so this is z equal to 1 actually, and z equal to minus 1 is somewhere here, that is minus 1 comma 0. So both are on the circle. Remember, whenever our poles are on the on the curve or inside the curve, then only we have to calculate residue. So in this case also we have to calculate residue. Only those poles which are outside the region, there is no need to calculate the residue for them. So in this case also we have to calculate that residue. We should say both the poles are like z equal to 1 and minus 1 are simple pole on the circle, on the circle. So they are on the circle. Whenever they are on the circle, yes, we should calculate their residues. And now R1 is residue at z equal to 1. So that is z minus 1 into fz at z equal to 1. So z minus 1 gets cancelled. We have sine square z upon z plus 1 only left at z equal to 1. So we get 1 by 2 of sine square of 1. Sine square of 1. Similarly, R2 you'll observe exactly similar one, minus 1 by 2, I'm writing similarly directly, minus 1 by 2 sine square of minus 1. But remember, sine of minus 1, we will observe sine of minus 1 is a minus sine 1 because we have that property, but two times that is coming. So this will come as minus 1 by 2 sine square 1 only. Remember, sine of minus theta is a minus sine theta, but the two sine functions are there. So 2 times minus sine, that become again plus. So R1 is 1 by 2 sine square 1, R2 is a minus 1 by 2 sine square 1. So by Cauchy residue theorem, integral fz dz over the curve C is 2 pi I R1 plus R2. And in this case, yes, R1 and R2 are the same with opposite signs, so it is a 0 again. Okay, so that about your Cauchy integral theorem or Cauchy residue theorem. So mainly focus on Cauchy's residue theorem. Majority of the times you have the example on that only. Okay, so thank you.